Thank you. Thanks to the organizer for giving me a chance to give a talk about my area. So the title is the Introduction to Affine Schubert Polynomial, but I will the talk will be basically the survey of what the area is about, which is called the Schubert calculus. So I'm going to start with introducing what this area is about. So Schubert calculus is one part of the enumerative algebraic geometry, and this question is the easiest question in the Schubert calculus. So let's try to understand this. So the question is as follows. There are four fixed lines L1 through L4 in the three-dimensional space. You can just imagine that we have lines on the R3. And the question is how many lines L intersect with all four given lines. So the answer, first of all, answer may depend on the line L1 through L4, but it turns out that if the lines are general enough, then the answer is finite, and the answer is equal to 2. So here is one example. So this example, we have L1, L2, L3, L4, and in this picture, the L1 and L2 intersect at this one point P, and L3 and L4 intersect at this Q. And the answer, the lines that intersect with the four lines are, one of them is easy to see. There's a line passing through P and Q, so it passes through all four lines. And another one is a bit tricky, but you can see that this pi1 is a plane that contains both L1 and L2, because two lines intersect in one plane, so there's a plane containing two lines. And same for L3 and L4, that pi2 contains these two lines. And another line, you can see that when you intersect pi1 and pi2, then this is an intersection. And you can check that this line intersects four given lines. So that's one particular example. But let's try to imagine that you move one of your four lines. So let's say you move this L1 to the little bit left, and then what's happening is that this two answer doesn't suddenly vanish or just gives a. It turns out most of the time the two lines, which is the answer, just moves continuously as well, so that the numbers are constant unless for some bad cases. So here's a statement. So the number of lines intersecting with the four lines in three space is 2 if the four lines are generic enough. I'm not gonna explain what this general position, but you can just take that as most of the time it just works. And that's what the Schubert studied, and that this became a Hilbert's 15 problem to rigorously define the theory that explains these multiplication numbers. Schubert considers also other different intersection worked on problems about intersection numbers, and sometimes are not clear, so that become a Hilbert 15 problem. And it turns out it's basically same as finding the structure constant of the cohomology of the Grassmannian, where the Grassmannian is the m-dimensional linear spaces in Cn, and a Schur function also comes into play. I will explain that later. And why the Grassmannian matter here? So because Grassmannian 2,4 when m is 2 and n is 4 is the same as the set of all lines in a C3. So here I draw examples. So Grassmannian 2,4. So let's say the ambient space is R4. Just assume that it's a real value. And I took a hyperplane, which is given by setting the last coordinate equal to 1. So that is isomorphic to R3. And when you take a random two linear space, in this case red plane, I just took a plane, and then intersection between this red and this given plane is a line. So you can identify the two-dimensional space in C4 and this line L in this R3. That's the identification. So this doesn't always hold, because, for example, you can take this red as a perpendicular plane to this, but that's why we need this projective space of three-dimensional projective space, but I'm not going to go into that. So an element in the Grassmannian can be written as a matrix, n by n matrix. In this case, this is GR. So we have a let's say we have a three-dimensional space in R C4, and then you can just write this three-dimensional space by giving us some bases. Let's say these are some bases, and you can each column is a vector in the three-dimensional space, and so if let's say you have a matrix M, and that is in the Grassmannian of M, n, if and only if these are linearly independent. That's fairly standard. And canonical form. So, I mean, it's possible that there are many metrics that gives the same three-dimensional space or m-dimensional space. So I need to. So what we can do is that you can just divide, for example, this element by some non-constant or multiply, or you can just add this and put another one. So basically, you can multiply the inverted matrix, and even after you multiply inverted matrix, then the result matrix give the same m-dimensional subspaces. So here is one example. So this form, I call this canonical form, but most of you this is also called a row echelon form in the linear algebra. So you just, so what we do is to just take the leading term for each vector and make this leading term 1. So we have a 6 times E1 plus 3 times E2. I just divide 3 by the element to get 2, 1. And when same here, and when there is so you have a E3 here, but we already have a leading term E3, so we can divide this by the half of this to get rid of E3. So that's the case. And then when you define a canonical form, let's call the position of this matrix as a column of the indices. In this case, 2, 3, 4. And then one can define a Schubert cell by the set of matrices in the n by n matrix, such that position of U is prescribed for given m numbers. You can define a CJ, which is called a Schubert cell, which is a matrix with a prescribed positions of pivots. And this is one example. In the Grassmannian 3,7, we have if J is 2, 4, 7, then we have a pivot positions at 2, 4, 7. And all the entries below 1 and the right of 1s are 0. And for the rest, you can put any numbers, any complex numbers. So what's the dimension? Dimension is just a number of stars. So in this case, we have a 4 plus 2 plus 1, so it's 7. So although I index the Schubert cell in terms of a subset of n, m subset of n, you can also describe this index set by reading the stars from the below. So 4, 2, 1, which is I will call partition. And the dimension is the sum of all the numbers in the partition, which is 7. And you can, so for any element in the Grassmannian, you can just, for any metric, n by n metric, you can just make a canonical form, then that should be in some unique Schubert cells. So Grassmannian is a disjoint union of the Schubert cells, where the index, I'm going to denote the index by partitions, where the partition is partition has to be inside m times m minus n. And so Schur variety is a closure of C lambda. It's a closed variety. If you don't know what the variety is, just think of that as a closed submanifold. And the one of the reasons why the Schubert varieties are important is because they form a linear basis of this. That's basically. So assume that if the coefficient ring is C, then as a C module, this is same as a C. Sum of C times the Schubert variety. Here's one example. So this is a variety or manifold we are interested. which is this is a subset of the Grassmannian 2, 4, where we collect all the lines P such that P intersect L is non-zero. So we fix L. For any L, we collect all lines that intersect L with some point. And it turns out that's a Schubert variety with a one box, just one. And what we want is to we have 4 given lines in the question, and so we can consider 4 different sets. And the question is the intersecting all for this object. Is that clear? If you have 4 lines, then for each line we have each set is a line intersecting with L is non-zero. So if the intersection, so what's the intersection of 4 set is a set of lines that intersect with that intersect with all of L lines. So 4 lines.
So what's the difference between CJ and C number?
Oh, they are the same. I just index it differently because partitions are. There is a bijection between this the M set of N and the partition inside of this. In the model language they use a partition rather than just fixing the numbers of the column indexes, because partition. I will explain more combinatorics of partition later. So you will see. They are just bijection.
So CJ is a set of. CJ is a subspace. Right?
Yeah, subspace.
But in the previous slide wasn't clear.
It's not subspace, it's a sub-variety. Subspace, I usually call a linear space, but this is sub-variety. Its degree is not 1. Yeah.
Grassmannian is set of.
Yeah, in this case, set of 3-dimensional space in 7-dimensional R7, for example. And this is a subset. Just a subset. Just imagine the 3-dimensional space generated by this column and this column and this column. Rows. Yeah, sorry, rows. And that's 3-dimensional space. And that's a subset. Yeah.
So how do you count the dimension?
Number of dots. This is just so partition is we have 4 stars on the bottom row, and there's 2 and 1. So yeah, partition is a decreasing sequence of integers. Yeah. Sorry for that. I have a definition of partition in later slide. Okay, I'll explain this. So, and the nice thing about the cohomology of the Grassmannian is that, in general, cohomology is that the multiplying, so let me clarify. So for any submanifold or closed submanifold in Grassmannian, there is a corresponding element in the cohomology ring, and the multiplication in the cohomology ring is the same as intersecting 2 closed submanifold. When they meet transversely, meaning that basically, that basically means it's like this. Not like this, basically. So the multiplication, the cohomology corresponds to intersecting. So if you assume that the answer is intersecting these 4 of this set, right, with a different L, and it turns out the answer that question can be interpreted as multiplying the Schubert Schubert class indexed by 1 and take a power of 4, and dimension of Grassmannian is 4, so that the answer should be C times a class that corresponds to 1 point. It's not. It shouldn't. It's just one 2-dimensional space, just one. So there's a constant C, and it turns out the understanding Schur functions is enough to compute this C. I mean, so if you, if this is too hard for you, then just remember this statement, because next slide I will do only combinatorics. So I'm going to define a Schur function. So lambda is a symmetric functions in the infinite many variables x1, x2, comma x3, blah blah blah, and a partition is a weakly decreasing sequence of positive integers. So in the previous example, we have a 4, 2, 1, and it generally satisfies this. And a partition can be shown, viewed as this called the Ferris diagram. In this case, corresponding partition is 5, 4, 1. You just read the number of boxes in the rows, each rows. And the given partition, you can define a so-called a semi-standard Young tableau, which is a filling of the natural numbers like this, such that for each row, the integers are weakly increasing, and for each columns, the integers are strictly increasing. And if the filling of the positive integers satisfies this condition, then it's called the semi-standard Young tableau. And there is a weight. Weight is just basically index the number of i's used. So number of one in here is 1. So this is first number. Number of 2 used is 1 is here. Number of 3's used 3 times, so it's 3. There's no 4, it's 0, so etc. That's the weight. And a Schur function is basically a generating function of the semi-standard Young tableau of the fixed shape lambda. So weight, I just explained the weight, and what is x to the weight is the definition is here. So x to the sequence a1, a2, a3, but means the x1 to the a1, x2 to the a2, x3 to the a3, and etc. So that gives you the some monomial in the some polynomial, and if you sum over all possible semi-standard Young tableau, then that is it turns out that's symmetric, and it turns out that has a lot of applications in other areas. Here's one baby example. When the lambda is the sequence of n boxes, then the condition under each this is n equals 4. So what's the condition? The condition is that the sequence, the positive integers are equally increasing, right? So that's basically condition. And I just wrote a corresponding the element. That is actually is called the homogeneous symmetric function of degree n, and is denoted by Hn. Schur function has a lot of application to algebraic geometry and representation theory, and actually Schur defined this function while he's studying representation of the GLN, but I'm not going to go into that. But so I'm just going to say, well, let's skip that part. And the one-up theorem is that Schur functions S lambda form a basis of the ring of symmetric functions. Any question so far about Schur functions? So here now I'm going to combine the cohomology of the Grassmannian theory and the Schubert functions. There is a surjective homomorphism from the ring of symmetric functions to the cohomology that just send the Schur functions to Schubert classes, as long as lambda is inside of the correct as long as lambda is the correct size. So note that this is a ring homomorphism. So multiplication of Schur function actually so let's say you multiply two Schur function and expand in terms of other Schur function. If you know what they are, then you can actually multiply to two Schubert class in the cohomology of the Grassmannian, which recall that the multiplication in the cohomology is basically intersecting two Soule manifold. And then the answer C is it turns out the answer C is just a coefficient of S2, 2 in S1 to D4. I will explain this part on the next slide, because I need to give one rule to compute what these are, which is called the Pieri rule. So the Pieri rule is the multiplication rule between the homogeneous polynomial of degree n and Schur functions, and then expand in terms of Schur function. Note that So Schur functions form a basis, so you can write it. And it turns out the coefficients are either 1 or 0, and the partition U mu occurs when mu's are obtained by adding a horizontal strip of size n to lambda. Horizontal strip basically means that you are just adding up boxes, but you're not allowed to add 2 boxes on 2 columns. That's what the horizontal strip means. But for our question, I'm just going to set n equals to 1. So when n is 1, mu can be obtained by lambda by adding a 1 box. Let me go back slide. So this question is, how do you get partition 2, 2 by adding a 1 box at a time? So here, there are only 2 choices. You add a box here, and after you add a box here, you have 2 choices. You either add this box first or this box first. And there are no other choices, so that this actually counts the coefficient of this in S1 to the 4. And so the answer is just 4. This is just saying that for Schur function, the multiplication of the Schur functions are well known. There are many combinatorics explain this constant in terms of Zeta-Kin, Yamanochi-Wirth, and some puzzles, etc. These are well studied. So that's basically a rough summary of what I just mentioned. The Grassmannian is a variety of m-dimensional subspace in CM, and there are nice Schubert variety indexed by partition in this rectangle, and you can get a geometric information like the intersection number in terms of combinatorics partition, like I just did, and the Schur function plays an important role in the Grassmannian case. Yeah, that's about, Any question up to here? No? Okay. The Schubert calculus, the early question I wrote is just the same question. And you can generalize this question to the following. You can ask how many points are in the intersection of Schubert varieties. Instead of just fixing a line, just fix some Schubert varieties. And one can also replace the Grassmannian by homogeneous space. Homogeneous space is a space, basically, roughly, the space is a group action. And these are a lot of typical examples: the Grassmannian, flag variety, and the simplicity orthogonal, like a homogeneous space for semi-simple Lie algebra, and Affine Grassmannian, Affine flag variety. There are a lot of, there are more than this. These are typical examples. So let's say we have a fixed object, like I say, we fixed one of them, and you can ask the following questions. So you can ask how to describe the cohomology ring of that space in terms of a quotient or subspace of polynomial ring. You call that Grassmannian. You can just, for the Grassmannian case, you can describe this cohomology ring in terms of quotient of ring of symmetric function by some Schur functions. And you can also ask a polynomial representative that correspond to Schubert basis. So basically, for GLN case, it's a Schur function. So the question is, for other varieties, what are the corresponding functions? That's basically the question. And also, this is a bit harder problem. So finding a structure constant, like a multiplication of this rule in terms of this function and coefficient, how to describe find a formula for this constant. So I'm going to do the same stuff for the flag variety. Flag variety is a set of n spaces and linear subspace such that dimension of fi is I. And it is nested, meaning that f1 is contained in f2, f2 is contained in f3, and etc. So for example, you have one point and a line containing a point and plane containing a line, and etc. And if you, that's called the flag. And the flag variety is the set of all the flags. Oh, well, also you can write a flag in terms of ordered basis where these fi's are vectors in Cn, and so fi is the span of the first I vectors. So here's one example. The flag can be written as like this, and this corresponds to the line. The two space generated by the first one and the second one is f2 and etc. And here again, you can have a different f's, different vectors that gives the same f. So we also have a canonical form for this case. In this case, so what can you do for the first vector? You can only divide or multiply by the constant because that first element gives a line. So I mean, you can only multiply up to constant. So here you have a 6,3. So you divide by 3 because the leading term of E2 is a C3. So you get 2,1. And for the next, you can divide or multiply by some constant, and you can also subtract sum of f1s. I mean, in this case, I didn't divide anything, but I only divide this vector by 2 to get 2, 0,1. And for the next one, there's a E3, and you can remove E3 by subtracting half of the second vector. So that the answer is like a 7 times E1 here. 7 times E1 plus there's no E3 plus E4, etc. And what I just explained is basically expressing this 4x4 matrix in terms of lower triangular matrices, meaning that all the upper side of the diagonals are 0, times some canonical form. So we have the same ones here. And the entries below 1 and the right of 1s are all 0. And that's just basically the same as the Grassmannian. And the flag variety is basically the set of all flags. And you can also write in terms of GLN, in this case 4. So GL4, the set of inverted matrices modulo this operation, the dividing or multiplying by set of lower triangular matrices. And you can define a Schubert set in the same way. So if you are given if you know that the position of the ones placed, then you just record the columns of each pivot, each ones. So you have we have a 1 on the first row at the second column. So we have 2 and 3 and 4 and 1. And in this case, this set is exactly the element in a permutation symmetric group. In this case, 4 is all permutation of in S4. And you can similarly define Schubert cell, and dimension is in this case 3, which is also same as the length of 2, 3, 4, 1, and it's generally true. And Schubert variety is also saying the closure of the Schubert cell. And okay, let me skip this part. I don't think I need this. So I just this part is important. So flag variety can be written as a disjoint union of Schubert cell, which was same as the Grassmannian. This is called product decomposition. And because of this decomposition, the cell decomposition, each CV is isomorphic to complex number up to some part, complex number to the some number, and that's the reason why each Schubert variety, the Schubert variety form a basis of the cohomology. In this case, the cohomology of flag variety. So each Schubert variety defines some cohomology class called the Schubert class, and I define a cohomology of the flag variety. And one can actually write this cohomology in terms of quotient of the polynomial ring. So this is just a polynomial quotient, a polynomial ring with the n variables, and below is symmetric functions. So H1 is x plus x2 plus up to xn, and that is just mode up by all the symmetric functions, positive or positive degree. And it turns out that's the same as that. And so that answers the first question. And you can also ask, what's the polynomial corresponding to this element, Schubert class? And also you can ask the multiplication of these two. But I'm not going to only explain the first one because the second one is open. So answer to the finding the polynomial, it turns out it's called there are functions called the Schubert polynomials, and they are due to many people.
What's the first question?
Oh, sorry. But first question is finding a polynomial, the element in here that corresponds to this element. So this is Schubert basis, formal basis in this left-hand side. So what's the question is, how to write this on the right-hand side in terms of polynomial? Right. And it's called the Schubert basis. It's called the Schubert polynomial, and it's defined as following. W0 is the longest element in the permutation, and for that permutation, the polynomial is like this: x1 to the n minus 1, x2 to the n minus 2, dot 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 x1 of sub n minus 1. And you can recursively define the Schubert polynomial degree 1 below by doing this divide difference operator, which is a divide difference operator f is f minus si of f divided by this constant. Si of f means that you basically swap the xi and the xi plus 1. That's the definition. And so the partial I of the Schubert polynomial for W is same as Schubert polynomial of a WSI, only if the length is decreasing. If that length is not decreasing, that has to be 0. So yeah, that's there's also interpretation of this operator in terms of geometry. So that's not random. So people study some geometric map between the flag variety, and it turns out this come up naturally. And Schubert polynomial corresponds to the Z of Schubert class of not W naught times W. Oh, which one? Oh, this? We know the Schubert variety for each permutation. Can you follow? So for each permutation, there is a Schubert variety, which is a closure of this thing. This is Schubert cell, take a closure, then you get a Schubert variety. And then, so if you have a closed algebraic variety, then there's a corresponding element in the cohomology ring. I'm skipping some steps, but that's basically true for this case. Yeah. Oh, here's one example. So assuming that I know Schubert polynomial for 2, 3, S2, S3, I can compute the Schubert polynomial for S2 by taking the partial of 3 of this polynomial. So this is same as the first term, and the second term can be obtained by the swapping all the x3 and x4. So in this case, there's no x4, so replace all x3 by x4, then divide by x3 minus x4, and you can show that this is actually polynomial because x1, x2 cancels out. X1, x3 minus x1, x4 divided by this is x1, and etc. That's the way to compute. You're starting from the largest element, largest polynomial, and just to follow this order. Follow this order to recursively define all the Schubert polynomials. And that's answer to the second question, and the last question is open actually. So if you have a two Schubert class or Schubert polynomial, and let's say you multiply, then you expand in terms of another Schubert polynomial, and it turns out these are non-negative from the geometrical reason, but it turns out that there's no combinatorial formula. Yeah, people just don't know in a general how to. I mean, one can calculate, but the combinatorial formula is that when you have a formula, the meaning of the combinatorial formula is that if you have a formula such that the formula itself is clearly positive, every terms are positive. There's no minus sign. Yeah, that's called the combinatorial formula. Yeah, that's about flag variety. Now I'm gonna move on to the affine Grassmannian, affine flag variety, but geometries are not easy enough that I can include any slide. So I'm just gonna explain what are the related combinatorics. I will try not to explain any geometry. Okay, let's just skip this. There's a definition of the affine Grassmannian. Let's set G equals the inverted matrices of determinant 1, and this means that this is an n by n matrix, right? Where each entries are either in R. What this means that we have an n by n matrix such that each entries are row rank series. That's what the first means. The second means that we have an n by n matrix such that each entries are power series. I mean, I just gave a definition. I'm not going to use it. Yeah. And it's the cohomology and the homologies of this affine Grassmannian is isomorphic to some subalgebra or quotient algebra of the ring of symmetric functions. So homology is isomorphic to lambda sub k, where the lambda sub k's are just subalgebra of the ring of symmetric function generated by h1, h2 up to hk. And this cohomology of the Grassmannian is isomorphic to the quotient of the lambda modulo the power sum symmetric functions, PM. PM is x1 to the m plus x to the m plus etc. It turns out one can realize this homology in terms of symmetric functions, and you can also describe there are also Schubert bases. And it's known that corresponding Schur bases are called the K-Schur functions and the affine standing symmetric functions.
Affine Grassmannian is also compact.
No, actually, affine Grassmannian is infinite variety. Actually, infinite variety cannot be compact. Yeah, I think. Yeah. Yeah, but that's some sort of thing. Affine Grassmannian is a weak homotopy to some compact group. Yeah, so that's the. Affine Grassmannian is known to be weak homotopy. This is a topology notation. Weak homotopy to the root space of the maximum compact set of G. In this case, S7. So K is SUN. And that's a root space. This is compact, root space is compact. So if you use topology, then this is isomorphic to the compact group. This is a group. So yeah, that's one of the reasons why people care about affine Grassmannian, because if you have a group, then the cohomology is a Hopf algebra. I didn't mention this Hopf algebra, but yeah, these are the Hopf algebra, not just a ring. Yeah, thanks for pointing it out. Okay, as I said, I'm just going to denote FL by affine flag variety without defining, but there are also Schubert bases as in the previous cases. I mean, the tau one is already something I explained. There are Schubert bases with the index by W, where the W is in the symmetric group. And for the flag variety, the index set is in the affine symmetric group, which I define in the next slide. And affine Grassmannian, cohomology of affine Grassmannian has a Schubert base indexed by affine symmetric group modulo just symmetric group. So my goal is to explain this in terms of ring of symmetric functions or ring of polynomials. Here's a definition of the affine symmetric group, Sn tilde is generated by the S0, S1 up to n minus 1 such that it satisfies the following. Si squared is equal to 1. Si, if J, I, and J's are adjacent, then Si, Sj, Si is Sj, Si, Sj. And if they're not adjacent, then they commute. You should note that if there's no S0, then this definition is same as one way of defining a symmetric group, not just not affine symmetric group, but just symmetric. If you delete S0, it's isomorphic to the symmetric group. So this strictly contains a symmetric group. And any element can be written as a word, like in Si, and a reduced word is a word of minimal length. Minimal length means that sometimes you can delete Si square or sometimes delete. So the reduced word of element is a word of minimal length. And the length of W is defined by that length. And that's just explained. If you get rid of S0, then it's isomorphic to the Sn. And the minimal cost representative, Sn tilde modulo Sn is an index set of the affine Grassmannian. Another way of saying this is that element is in this set if and only if all the reduced word of W ends with S0. So that's a set for the affine Grassmannian, and the whole this affine symmetric group is an index set for the affine flag variety. And it turns out that there's a nice decomposition of the cohomology affine flag as a tensor product of affine cohomology affine Grassmannian and the cohomology of the finite flag variety. Maybe I'm not going to describe what this injection is. So let me just point out that this injection is obvious. Injection from here to here is very obvious, and it has been known. But this one is a bit tricky. That this is basically part discovery. That there's some way of embedding this cohomology of finite flag to here under some modification. Okay, so now I'm going to describe this in terms of polynomial. Since we already showed you the how to write this cohomology of the finite flag and a cohomology of the affine Grassmannian in terms of polynomial. So this one is for flag variety. J integers are x1 through xn, and you divide by all the symmetric functions. And the cohomology of affine Grassmannian correspond to the just polynomial ring generated by the ring of the power sum symmetric function up to n. Yeah, this case n minus 1. Yeah, this is n. And then this cohomology of affine flag is a tensor product of these two rings, and you have this generator is x1 through xn. These are degree 1, and we also have generator p1 through pn minus 1. But these are degree of pi is I, as you can see, power sum symmetric functions of degree I. So these are degree pi's of degree I, and we only have a relations between the xi's, but no p's. And I'm going to define the so-called Affine Schubert polynomial using the same analogy. So recall that when I define a Schubert polynomial, I use this divide difference operator called partial I. So partial I of f is f minus si of f divided by xi minus xi plus 1. That's recall this one. So my goal is to generalize this operator to affine setting. I mean, as an operator on this ring, the bigger ring, which provide the affine Schubert polynomials. Pure definition, but the number 1 and number 2 can be just calculated from this definition. It's nothing surprising. This 1 and 2 has been known, so meaning that we know how to act Si of xj because it's the same. So Si swap the xi and xi plus 1. That's basically it. And this has a correspond. I mean, there's an action you can just calculate this divided from the partial I of xj. So number 1 and 2s are already known. So number 3 and number 4s are something I found, which is an action of the Si and the partial I of Pm. So when I is non-zero, then Si does nothing. The Si of Pm is just Pm, and the partial I of Pm is just 0. So it does nothing to the P's for non-zero I. When I is 0, then there's some weird form. So S0 Pm equals to Pm plus x1 to the m minus x0 to the n. So I'm going to give a better way of explaining this. It's a bit of cheating, but I like this way. So just think of these power sum symmetric functions in the variables x0, x negative 1, x negative 2, etc. So just think of power function as a power functions in the negative variables, starting from x0, x negative 1, x negative 2, and just try to act as 0 on it. Then what this does is that it replaces x0 by x1, right? So x0 swaps as x0 and x1. So it basically just changes x1 to x0, as x0 to x1. It does change nothing. And when you write in terms of this again, then it's a Pm plus we added the x1 to the m, and you subtract x0 to the m. That's basically what's going on. So for the affine flag, we have two components. Like we have a p symmetric functions in power sum symmetric function. Just polynomial in power sum symmetric functions. On the flag variety, we have some xi's. And it turns out that finite part has a variable x1 to xn, and the affine Grassmannian has a variable x0, x minus 1, x minus, and infinite many. And these parts are symmetric, but this finite part doesn't have to be symmetric. That's basically what's going on. And then you can define a affine Schubert polynomial that corresponds to Schubert basis as a solution of this operator. This partial I of affine Schubert of W is affine Schubert of WSI when the length only decreases by 1. If not, it's 0 otherwise. And we also impose condition that degree of affine Schubert polynomial for W is L of W. And initial condition is that the identity is 1. If this equations uniquely determines a solution, and the answer is called the affine Schubert polynomial. Okay, there are better ways to define affine Schubert polynomial, but that requires other stuff that takes a lot of time. So for example, I need to define affine standard symmetric function, but I don't have time. So this is probably that best description. So for now, just recall that this equation is basically the same as I showed in the finite flag variety case. And the theorem is that, so this affine Schubert polynomial is indeed matched with the Schubert class. The Schubert class in this cohomology ring of the affine flag variety, and these polynomials are in this ring, Rn. Rn is I forgot, this is Rn. Yeah, this is Rn. This ring. And it turns out that this affine Schubert polynomial strictly contains other important functions. The Schubert polynomials are one of them. Schur functions are included in the Schubert polynomial. So Schur functions are also included. And there's also called the affine standard symmetric function that is studied for the studying affine Grassmannian by Thomas Lamb. And it turns out how they encode the affine Schubert. Let's say we have one affine Schubert polynomial. That's a polynomial in the xi's and pi's. If you set all xi equal to 0, then affine Schubert polynomial become just affine standard symmetric function for W. When you remove when you set all the pm's equal to 0, then the affine Schubert polynomial becomes a Schubert polynomial. If this W does have some S0, if the W is not if W cannot be considered as a permutation in the finite symmetric group, then this is 0. They're just 0, just vanish. When there's a, yeah. And here's one example. Yeah, these are just some list of the examples. So Affine Schubert of SI is like this. When you set P1 equal to 0, this is a Schubert polynomial for SI. When you set xi equal to 0, P1 is a affine standard symmetric function for SI. And that holds generally. So this case, when you set xi equals to 0, then we have H2, that's a affine standard for S2, S1. When you, so I use a homogeneous instead of power sum. When you set OHI equal to 0, we have a x1 squared, which is a ordinary Schubert polynomial for S2, S1. And the reason why I introduced the symmetric functions with the negative variable is as follows. So one can write this in a better way. So if you believe that homogeneous polynomial of H2 is a homogeneous polynomial in terms of x0, x minus 1, x minus 2, etc., then this is just a homogeneous polynomial with the x1 added. This, when you expand this in terms of x1 part and the negative x part, then this becomes this. So although I define it defined in terms of divide different, which may look weird, but this actually has a lot of combinatorial structure. And these are just some list of known stuff. The HM times Affine Schubert and the PM times Affine Schubert formulas are known by myself in 2004 and 2005. And for general multiplication, it really is very hard. And there are actually a lot of work has been done about Schubert polynomial since the discovery of Schubert polynomial, because that Schubert polynomial is defined on the 1970s, so it passed like nearly 4 years. A lot of algebraic combinatorialists studied this Schubert polynomial. So you can actually, if you have a sum of your favorite theorem about Schubert polynomial, you can try to generalize to the affine version. I don't know a lot of that for this question. And these are some of ongoing research. You can define affine Schubert for other types, because this decomposition theorem is true for other types, other affine types. Yeah. And also, you can replace cohomology by equivariant version, equivariant K-theory, quantum cohomology, etc. There are a lot of work needs to do. And there's also a nice way of writing affine Schubert in terms of affine standard and Schubert polynomial. And but I won't explain that. And this is also this is basically same as equivariant version of the affine Schubert polynomial, the last one. Okay, thank you.